In this lesson, we're going to look at characteristics of waves. So we're going to start with the frequency, then we're going to go into the period, amplitude, and talk about the wavelength, and then also what the wave speed is. And we'll conclude this by talking about the wave equation. So if we were to take a wave, and we just say it looks something like this, and this would obviously repeat for a long period of time. I need to know where my center point is. So this line here would just be like, kind of like a zero. If I was to call this my y-axis, this would be like the x horizontal line. So this would go in both directions. So the first piece we're looking at is the frequency. So frequency is measured in hertz, and we use the symbol Hz to symbolize hertz. Frequency talks about how many times the wave passes by a certain point every second. So if I was to look at, say, this point in time, and I was watching this wave move across, and I counted every time it goes from there back to there in 1 second, that would be the frequency. So for example, if I had a separate case and I looked at this, and from here to here was 1 second, and the wave looked like this. So it went so say this is my wave. I can see that from here to back here, this is one wave. And then therefore from this point to this point would also be one wave. So if I looked at how many waves have passed by in 1 second, I've got 2 waves in the time of 1 second. So this would have a frequency of 2, or using my units, I would call this 2 hertz. So that's how we define frequency. It's the number of times a wave passes a point per second. Now if I was to look at the period talks about how long does it take for one wave. So previously in my frequency example, I looked at how many waves passed in a period of time that was set. So in 1 second, how many waves passed. Now when I'm looking at period, I'm saying how long does one wave take? So if I go from this point, I do half a wave back to the start, a wave, my period is, what is this time? This would be period. So it's the time it takes for a single wave. Similar but slightly different to your frequency. This will make a little bit more sense on how we can calculate this once we've done the wave equation. Now if we look at amplitude. Amplitude is thinking of how much energy it has, or if you're talking about sound, amplitude is analogous to the volume. So if you have a bigger amplitude, you've got more volume, the sound itself will be louder. When we're talking about a general wave, amplitude is how much energy it has. If you create a very high energy wave, it's going to have a much bigger height, which is its amplitude. So an amplitude is measured from the highest point to the center, or because it's a symmetrical wave, it would also be the center to the lowest point. These distances would be equal. And we use the symbol capital A to simplify or symbolize amplitude. So distance is amplitude, the time for a single wave is your period, how many times a wave passes per second is your frequency. So I could write in here per second, period is a time in seconds, amplitude depending on the unit could be meters, could be centimeters, could be millimeters, micrometers, depends on how big our wave is. So speed now. Speed talks about if the wave is propagating in this direction. So this is the direction of the wave. Remember, if we're talking about a transverse wave, the crest and trough is actually moving up and down, perpendicular to the direction, but the wave itself is traveling in this direction. So when we talk about the speed, we're saying how fast is that wave traveling? The frequency is how many times per second, period is how long for one wave, Now the speed is literally how fast is the wave traveling. So if I have a source here, and this is, say, my speaker, or it could be a torch, whatever, and it's creating this radiating wave of light or sound. And remember, it's obviously traveling in every direction, like so. The question is, what is the velocity in meters per second of this actual wave? And I could use this to then say, well, if I know its velocity and I know how far away I was over here, how long is it going to take me to actually hear it? And I'll use little t for this so we don't get confused with period. So this is where we go back to the basic motion formulas. We can relate the waves to the motion based on the speed. So this is just the speed of propagation. How fast does that wave travel? This will change depending on the medium. So just like when we talked about the speed of light through objects, even though the speed of light technically never changes, the time it takes to travel through an object changes. So here we can talk about the velocity of a wave is dependent on what it passes through. So if it's traveling through air, that might be great. Suddenly it hits, and we'll just call this a water layer, or it hits the water surface. Once it gets into water, if this was sound, for example, it travels faster in water. So the velocity would increase. So I've got this higher velocity in water than a velocity here in air, which would be slightly less. So again, we're just talking about the speed of the wave. The wavelength itself, this is talking about the distance between the start and the finish of the wave. So how long does it take in a distance, not a time now? What is the distance from here? And this can be measured in, again, meters, centimeters, nanometers, depends on how big our wave is, what the frequency is, etc. Notice that here I've gone from start to finish, or start to the start of the next wave. But I could equally go from here to here. This would also be the distance. I could also go from the trough here to the trough here, and this would be distance, or wavelength. So it doesn't matter, as long as I'm going from point to point, start to finish, start to start, crest to crest, trough to trough. I could go halfway between, and go here to here. That's fine too. All of these things will give you the exact same distance, and this is the wavelength. So it's the actual physical length from one point in the wave to get back to that point in the wave in a horizontal line. Wavelength, we use the symbol lambda. So this is the Greek letter. This is the symbol for wavelength. So the wavelength would be equal to X amount of meters, for example, could be nanometers, etc. But we use that symbol. So frequency, we have the hertz, period, we use a capital T to symbolize time. Capital T tells us period, not to be confused with a lowercase t, which is just talking about a time in general. Amplitude, we use a capital A. Speed is just a velocity, so you can vector that if you want. And wavelength is our lambda. So these are our key components that make up waves.